Hello, everybody. My name is Howard Wheater. I'm going to talk today about hydrological modeling for water resources management in arid areas. It's a very great pleasure to be speaking to this meeting. I was awarded the Prince Sultan bin Abdulaziz Prize in 2006. It was a great honor, and I've also been privileged to serve on the Prize Council since that time. And I'd like to pay tribute to Prince Sultan bin Abdulaziz for his inspiration in developing the prize and for his memory, which continues, and for his son, Prince Khalid, who continues to give great leadership to this program. So I'm going to take you back to work that I was doing in Saudi Arabia a long time ago in the 1980s to address some issues around water management in arid and semi-arid areas. These are the regions of the world, as we all know, where water is most scarce and most precious. But what we often fail to remember is that the hydrology of these areas is really very different from humid zone hydrology. And there are challenges of scientific understanding and major challenges of modeling. In most of the world, in humid areas, we use hydrological models routinely for many purposes: flood forecasting, water resources design, water resources management, coupled modeling of different kinds, linking with sediments and water quality and ecosystems. But most of the models that are used are really not well suited to application to arid areas because there are particular challenges and particular difficulties which yet have to be overcome. So I'm going to really present those challenges and talk to you a little bit about the way forward. So one question is, how useful are hydrological models for arid and semi-arid areas? And another question, what are the future needs and challenges to improve our capability for managing water in these areas? So one of the main challenges of arid areas is limitations of data and limitations of detailed studies. There's one watershed in the world which is famous. It's called Walnut Gulch. It's in the south of Arizona. And that's been monitored for well over 50 years now as an experimental basin. And there really is nothing to match that anywhere else in the world. But in the 1980s, I was privileged to be part of a representative basin study in the southwest of Saudi Arabia. This was a pioneering initiative that studied 5 basins ranging in size from 500 to 5,000 square kilometers. And it was funded by the then Ministry of Agriculture and Water. I think it's an important study and one that's played an important role, but I'm going to argue at the end that we really need more studies of this kind to bring this work up to date. So this is a very beautiful part of the world, as many of you will know. We have mountains draining towards the Red Sea, and the traditional use of water resources is to tap the groundwater that's in the Wadi alluvium. And you can see the bottom picture, a traditional well, which is located in the bed of a Wadi alluvial system. So a few important points about this study. First of all, we had 100 rain gauges spread over these basins. Each basin had a very detailed weather station, as you can see in the second picture. There were many flow stations and groundwater observation wells. And the picture on the right is an interesting one because you'll see that there's a float recorder located at a very great height above the bed. And that's because the first time this instrument was installed, it was washed away by a flood that came down this normally dry channel of around about 3,000 cubic meters per second. That's a huge amount of water coming down the system. So that tells us that floods in these areas are important, but they're also potentially very dangerous and very damaging. And in the flood season, it's common for people to suffer damage and sadly sometimes for there to be loss of life. Another important aspect of this study was that each of these 5 basins had permanent teams of observers living in the basin, and that was really crucial to data quality. So various things can be rather simply shown from this work. I'll just show you a few photographs. First of all, when we have intense rainfall, we get very extensive generation of overland flow. This happens very rarely in other parts of the world. Obviously, for urban areas, we get a lot of overland flow, but to have such extensive overland flow is not common, and it gives a very rapid response. Another important aspect is that we've got intense rainfall falling on bare soils, and those soils tend to crust and give us more runoff than we would expect. And then we have flash floods being generated. And this is an interesting picture because if you look at the sky, you can see that we have a clear sky, cloudless, and yet we have a flood wave moving down this dry wadi bed. And I'll just show it progressing down the system at roughly a jogging pace. So this is the nature of the water resource, because this flow infiltrates into the wadi bed, and that provides groundwater, which can be used for a variety of purposes. And the bigger the flow, the further it travels before it infiltrates. And this flow characteristic gives us a major challenge, because when we measure flow at a gauging point, we don't actually know how much water has traveled upstream. In fact, we may have no flow observed because all of the upstream flow has infiltrated. So this is a big challenge for interpreting flow data. This slide shows the processes of channel bed infiltration. This is at the end of a storm, the end of a flow. You can see there's quite an extensive flow in a large channel. But if we dig a little pit next to this flowing channel, it's unsaturated. So what we see is that this flow, which is on a very permeable substrate of wadi alluvium, is actually perched. And if you look carefully at the photograph, you can see there's a layer of sediment that's been deposited, and this is maintaining that flow. So after a day or so, this flow will dry up, the temperatures will rise, the fine sediments will dry out, crack, and then disperse, and then we'll be back to a permeable channel. So if we do measurements of the permeability of this channel bed under dry conditions, it will be very high, and yet you can see that towards the end of this flow period, we have this perched water flowing. So there's some important issues around the interaction between surface flows and groundwater recharge, which still are not well understood. I'm going to turn now to rainfall, because that's a major issue for these areas. So this is a picture which shows snapshots of sequential hours of rainfall in a basin called Wadi al-Leith. It's about 3,000 square kilometers. And the first hour is in the top left, and then the second hour, and the third hour, and the fourth hour. And you can see that most of the rainfalls recorded as 0, but in the first hour, there's a burst of rain at the top right hand of the diagram, the northeast corner, up to 17 millimeters in an hour. The second hour has very little rain. The third hour has a burst of rain in the center of the catchment, again up to 19 millimeters. And then the fourth hour, it's dissipating. So we have a very, very spotty picture captured in the daily summary. So the order of half of these rain gauges observed no rainfall. So this is one of the major challenges for us in trying to model this system. It's not uncommon for rain to fall between rain gauges. You have no rainfall observed, and you have a significant flow. And that's a real challenge for any hydrological modeling. This is a diagram that shows response of one of these basins moving from the top of the basin to the bottom, and we can see groundwater levels and some surface flows. And at the top, we have a distinct rise in April, as you can see, of groundwater level. But if we move down to the bottom of the catchment, there is no response apparent in that groundwater system. So we can take groundwater measurements at the base at the bottom end of this water system and apparently see no record of the recharge that's taken place upstream. So it's not only surface flows that are problematic, we also have to think very carefully about groundwater data. And then there are some little conundrums. So this is a diagram that plots total rainfall volume for a set of storms against the total runoff volume. And if you look carefully at this diagram, you can see that the largest runoff volume comes from one of the smallest rainfall volumes. So this is again because the rain gauge network, although quite dense by conventional standards, is failing to capture the precipitation in its full spatial extent. So we have a set of really critical process issues which are very problematic and difficult to address. First of all, extreme spatial variability of precipitation. I've shown that here. If you look at the literature from Walnut Gulch, you can see it even more dramatically. Secondly, we have these runoff generation processes. So extensive overland flow can occur, but crusting can affect the soil properties, give us more runoff than we think. We've got these complicated processes of losses of flow to the channel bed, which we can call transmission losses. They're affected by all sorts of factors. We tried to measure this in the field. When people have put instrumentation into the field, it's usually lost because the floods are so damaging. The floods mobilize the sediment in the bed. But as we've seen on the recession of the hydrograph, as the flood is passing, we get this deposition of fine sediments. So it's a very complicated set of processes which determine how much water is recharged to groundwater. And then the groundwater recharge itself, of course, depends on the subsurface topography. And I've done work based on the Saudi data that shows the effect of lenses and layering in the alluvium, the legacy of previous floods, and how that affects the recharge process. So there's a set of real challenges there, and we still don't have a lot of good science to really understand and quantify some of the processes at small and also at large scales. I'm going to very briefly take you to the Sultanate of Oman and a little study that illustrates some of these, modeling a flood response in Wadi Ahin. This is a wadi that's quite small, it's 800 square kilometers, had a major flood, as you can see. It flows from the mountains to the Gulf, to the Batina Plain. So this was some work done by Aisha Al-Qureshi, who was a PhD student of mine and a director of the Ministry of Water Resources in the Sultanate. So we worked with a model called Kinross, which is one of the few models in the world that's really been specifically designed for arid areas. It's developed by the US Department of Agriculture, David Woolheiser. We had data from 29 events. So here's an aerial shot of the catchment. The right-hand diagram at the top shows us the distribution of rain gauges, which is really quite dense by any standard. The bottom left-hand side shows us how the Kinross model operates. It represents the catchment as a series of plains which can infiltrate and generate overland flow, and that feeds a set of channels which can generate runoff and also infiltrate. And on the bottom right, we can see how the catchment is split up. So the first thing to note is that even with this network of rain gauges, how we represent the spatial rainfall makes a huge difference to the modeling. So what we see here are different ways of interpolating the rainfall, and they give very different modeling results. This is a particular event, and we can fit a model to overland flow, to peak flow, or we can fit a model to the runoff volume. we get different parameters and slightly different results. But the bottom diagram here is probably the most interesting, because here we've got the best parameter sets taken from each of the 28 events and applied to this particular event of the 11th of March. And you can see how different the results are. So it's very difficult to get a representative set of parameters, really because of these problems mainly to do with spatial rainfall. And here is a diagram that shows the performance fitting to minimize the difference of the observed and simulated flood peak and difference between observed and simulated flood volume for each of these events. And there are different strategies for selecting best parameter sets. And if you take the ensemble average of the best parameters for each individual event, you can get wildly inaccurate results for some. And really what we did here was take the best parameter set fitted to all of these events. However, if we look at the data, there's some interesting effects that are apparent. So the top left diagram shows the flow volume plotted against the total rainfall, and it's a tight relationship. And similarly, the second left diagram below that shows the flow peak plotted against total rainfall, and again, it's quite a tight relationship. So simple regression does quite a good job, really better than a distributed hydrological model, in representing the relationship between peak flow runoff volume and rainfall volume. So there's some important lessons to be learned here about the use of models and the use of basic data analysis. So just to make some concluding observations, water resource management and water management, flood management also in arid areas is a huge challenge. We need hydrological models. What I've tried to show in this very short talk is that modeling is really a very difficult challenge. There's a lot of work needed to improve our scientific understanding of these processes and to develop appropriate models and modeling systems, and particularly handling this issue of spatial rainfall. We have to think very carefully about that and think about using stochastic methods that can represent the uncertainty in the spatial rainfall. So we need, first of all, improved science, and that has to come from comprehensive studies on experimental basins. So I've shown you a really important study from Saudi Arabia in the 1980s. The sad thing about that study was that the basins were stopped at the end of the 5-year period. We really need detailed monitoring at an intensive level, operating for years and decades. And as I said, the only basin that's done that for arid areas is a small basin in Arizona, Walnut Gulch. Second point is good quality data is really difficult in these harsh environments, and particularly flow data. Flow measurements are quite difficult. I showed you the picture of the flow gauge that was originally washed away and then reconstructed. We need to develop expertise at a local level and a regional level to understand the science and develop and apply appropriate models. And I think there's a huge role to share information within and between the world's arid regions. And I was one of a number of people who developed a program for UNESCO called GWADI, which focuses on the world's arid regions. And that's done quite a lot of work to bring people together and share knowledge and information. And I'll finish with showing you a couple of books that have come out of that program. Now, it's a long time since I was working in Saudi Arabia in the 1980s. And the last decade, I've been working in Canada as a Canada Excellence Research Chair. And I've now retired from Canada, but my last major initiative was to bring the Canadian research community together to address their hydrological challenges, which are really all about cold regions, cold processes, frozen soils, snow, ice, retreating glaciers, and so on. So there were 4 universities that led this program and another 14 universities involved. So we had 18 universities. And we had a grant of about 80 million Canadian dollars. And with supporting money, we had a program that was originally about $140 million. It's now grown considerably with additional inputs from government agencies and industry, as well as the universities themselves. And this has brought people together to address problems that are particular to cold regions in Canada and elsewhere. And at its heart is a set of large-scale observatories, so we can monitor and understand the scientific processes and then apply that knowledge to modeling. So there's a very strong argument that I'm making that we really need an initiative that's big scale and ambitious to take our hydrological understanding forward for areas of the Middle East and other related arid and semi-arid regions. So just to close, if you're interested, there are 2 books that came out of the UNESCO program, one on hydrological modeling and one on groundwater modeling, but you'll see they're both more than a decade old now, and that work really needs to be updated. And you can check out the GWADI website, which has further information. And then there's a list of papers to some of the work that I've been doing in semi-arid areas, which really led to the award of the Prince Sultan bin Abdulaziz Prize. So thank you all very much for your attention. It's a great pleasure and privilege to contribute to this meeting, and I hope you found this short talk of some interest. Thank you.